Okay, so what we're going to do, instead of completing chapter 15, which start to be really complex and getting really deep into analyzing the transistors, what we're going to do is skip ahead to chapter 17. And the reason being is that I think chapter 17 is more practical in application. But I do suggest, for your own personal knowledge, you should read the rest of chapter 15. Okay, so chapter 17 is going to be on the frequency responsive amplifiers, which is something that probably going to be more applicable to the field you guys are going to get into. Okay, so for lecture 33 review. So we started getting into going from transistors to transitioning that to operational amplifiers. And we found out, or we discussed some important applications of the differential amplifier is at the input stage. The one important application of the differential amplifier is at the input stage of the operational amplifier. And this differential amplifier provides desired differential input and it rejects the common mode. And op-amp usually requires higher voltage gain than is available from the single differential amplifier stage. And most op-amps use at least 2 stages of gain. And also that third stage at the end, which is used as the output stage, it provides a low output resistance and high output current. And so we started looking at this right here, which is the 2-stage prototype for op-amp. And we looked at this DC equivalent circuit. And of course, what we did is we replaced the source right here, which was that resistance, with this type of source for DC, which is something that we're getting into. But to continue on, go ahead and read the rest of chapter 15 if you'd like to get into that. But for now, we'll go into chapter 17. And this will be the last chapter we cover for the course. And today we'll cover amplifier frequency response, which is quite familiar to you guys, except we'll break it up into high, mid-band, and low frequencies. And also we'll get into the determination of low frequency poles and zeros and for the common source amplifier. Okay, so amplifier frequency response. So previously we discussed the analysis and design of mid-band characteristics of amplifiers and the low frequency limitations due to coupling and bypass capacitors. And what we did previously, we neglected the internal capacitance that limited the response of high frequencies. So what we'll do now is complete the discussion of the basic amplifier design with the introduction of methods used to tailor the frequency response of analog circuits at both low and high frequencies. So remember, this is the mid-frequency, the mid-band, and over here is the high band, and below that is the low band. So here's a cutoff frequency for the low frequency and a cutoff for the high frequency. Okay, so in this Bode plot right here, this Bode plot, as we've discussed before, it can be written in terms of a numerator and a denominator in terms of polynomials in S, right? So from here, you can factor this out and get the zeros, and from the denominator, you can factor that out and get the poles. And what we'll find out is that these right here, the WPs here, here, and here, and here, those are the poles, and the zeros are like right here and also right here. And so from what we figured out previously, what the poles do is that they sort of take your trajectory and bend it down by 20 decibels per decade for each order, and the zeros will bend it up by 20 decibels per decade for each order. Okay, so you see here where the poles are, they're bending down here, bending down here, bending down here, and bending down right there. And the zeros, they'll bend up and bend up right there. And in this low frequency and high frequency, those cutoffs, that's at 3 decibels down from wherever the max is, right here. And that's how to measure those. And this range right here, we'll call this the low frequency, that F of L. And then this range over here, we'll have this factor be FH, the high frequency. Okay, so what we'll do is we will rewrite this part right here as 3 factors. This will be the gain A mid, this will be the low frequency factor, and this will be the high frequency factor. Okay. Now this low frequency FL, it could be written like this, right? So this piece right here will just take care of this portion of the Bode plot. And this factor right here will take care of the high portion of the Bode plot. And we will write this in such a way such that when the frequency in S, when it gets really high, like higher than omega L, then this whole factor right here becomes 1, right? So that will become 1. And then in this range over here, it will just be A mid times FH, okay? And in this region right here, this part right here will become 1. And so that goes away. And then this piece right here could be written as A mid times FL. Okay, so to do that, FH is chosen so that its magnitude approaches the value 1 at frequencies well above the upper cutoff frequency right here. Okay, so that's written out explicitly. And so at low frequencies, the transfer function becomes this, where remember that F of H is approximated as being 1. And the same thing happens on the other side too, where for FL, that's chosen so such that its magnitude approaches the value of 1 at frequencies well above the lower cutoff frequency, omega L, right? And so its high frequencies, this value of AV, that actually becomes A mid times F of H in this region over here. And then we'll piece those two together. Okay, so it says in mean designs, the zeros of FL can be placed at frequencies low enough to not influence the lower cutoff frequency, omega L. And one of the low frequencies, one of the low frequency poles, let's call that omega P2, it can be designed to be much larger than the others. And so if you have those kind of conditions, then you can approximate this portion of the transfer function as this right here. Okay, and so that's looking at this piece right here, where this is like omega P, and this is considered to be much larger than the other frequencies. So you could think of it like this, and this is called the dominant pole. Okay, so this pole omega P is referred to as a dominant pole if you have that condition, and the lower cutoff frequency omega L is approximately equal to omega P2, and so that's what's happening right here. So this omega L is approximated to be omega P2, and this is the dominant pole right here. So if a dominant pole does not exist at low frequencies, then the poles and zeros interact to determine the lower cutoff. Okay, so that's what we'll do in this case. And so here's an example of having 2 zeros and 2 poles at low frequencies. And so your amplitude is approximated as this. So remember your F of H, FH is about 1. Okay, so we'll just take it as A mid times FL. And so we can write it like this. So you have 2 zeros and 2 poles here. And then we take the magnitude of that. And when we take the magnitude of this, you are taking this and multiplying it by its complex conjugate and then square rooting it. So what happens here is that the square root of a mid squared is just a mid. But this right here becomes the square root of this times its complex conjugate. And remember what happens with the complex conjugate, right? So these j omegas that are in here, they become negative j omegas. They cancel out. Those cross terms cancel out. So what you have is that each of these terms just becomes squared. So this s right here just becomes omega squared. This omega z1 becomes omega z1 squared, and so on. So that's where this expression comes from. Now, at lower cutoff, we know that it's going to be 3 decibels down, which is a mid divided by square root of 2. Okay, so if we look at this particular frequency of omega L, and we relate it to this expression right here, we can clearly see that if we plug in omega L here, we're going to get this omega mid, which is right here, times square root of 2. So that just means that this expression right here must be equal to 1 over square root of 2, which is, so we're going to assign that here. And then from this, you can square both sides of that. So this 1 over square root of 2 becomes 1/2. This expression, if you square it out and expand it, it looks like this. You can also divide the top and the bottom by omega L to the 4th, right? And then you have these terms right here. Now, you can sort of eliminate these terms if you can assume that this omega L is larger than the poles and zeros, those frequencies. And then, so those terms right here, those two can be neglected. And so you can say that 1/2 just equals this stuff right here divided by this stuff. And if you solve for omega L, which is right here and here, you are able to get this expression right here. Okay. And again, that's due to eliminating these two terms. Okay, so so in general, just looking at this, you can see that the two poles are just squared and added, and the two zeros, they're multiplied by 2. They're also subtracted from these, and they're squared. Okay, so what you can do is then extend that to a number of poles and zeros, and so that just becomes a sum of omega of the poles squared minus 2 times the sum of the zeros, those frequencies squared. So this is in general right here. Okay, and we can also do that for the high frequency. Okay, so so in the region greater than midband, AV can be represented by high frequency approximation like this, and in this case, the FL is approximated as being 1 for high frequencies, meaning the zeros of FH are often high enough in frequency that they do not influence the value of this of FH near omega H. In addition, if one of the pole frequencies is much smaller than the others, so this is like the opposite case of the low frequencies. If it's much smaller, then that is the dominant high frequency pole, and that exists. And then you could approximate your FH as being this expression right here. And so you could think of it like this. So this dashed line right here is your FH. And so you could, now the solid line is the actual, right? But you could approximate your actual by just, using that, and that just looks like that. Okay. So for cases of dominant pole, the upper cutoff frequency is given by this, where omega H equals omega P3. So in that case, let's go back to our other plot. We're talking about like right here. Okay. So omega H is about equal to omega P3 here. And this plot right here This piece right here is the approximation of this plot right here without the low frequency, right? Because we're only looking at this portion of it, okay, where omega L is 1 in that case, right? So if a dominant pole does not exist at high frequencies, then the poles and zeros interact, and then you could use that to determine omega H, okay? And here's an example, again, using 2 zeros and 2 poles, but now we're going to do it at the high frequency. So in this case, your AH is equal to your A mid times your FH. Here's your A mid. Here's your FH with your 2 zero products, your 2 pole products right here. And then you take the magnitude of that. So you do a square root of complex conjugate of this. You get this expression right here. And then you look at the lower cutoff frequency, like before. So you set that equal to its maximum over the square root of 2, because it's 3 decibels down from the maximum. And then you identify this with that. And so this 1 over square root of 2 must equal to this expression. So setting this equal to this, then what you do, you can square both sides and solve for omega H. And if you do that, you end up with this expression right here. And then for general and poles, it's just a sum of these omega P's minus 2 times the sum of these omega Z's right here. So very similar analysis, except you're using the poles instead of the zeros. Okay, so let's get into the low frequency of the poles and zeros on amplifier. Okay, so let me ask you a question. For this amplifier right here, why is this amplifier a common source amplifier? What was that? Yep, exactly right here. Exactly right. You guys see that? So if you would have redrawn this circuit in AC domain, right, this bypass capacitor right here would have shorted that, and so this would have just went directly to ground, right? Of course, that wouldn't be there, that wouldn't be there, and this would just be a short circuit to ground. So yeah, and typically, in order to sometimes to see that, you actually do have to put it in the AC domain by getting rid of your capacitors, where you have the anyway, so to apply the above analysis, we typically need to know the poles and zeros. The frequency response of an amplifier can always be calculated by analyzing the circuit in the frequency domain. If you know the circuit, you can actually see it. Now, if it gets too overly complex, what people typically do is just use a tool like SPICE, right? But a circuit like this, you can do this with hand analysis, but for more complex circuits, you want to use SPICE. And also, typically people are really interested in the lower cutoff and the higher cutoff only, a lot of times. Okay, so we're going to start developing some analysis, some methods to just approximate the low frequency cutoff and high frequency cutoff. Okay, and we'll use this common source to do that. So first what we'll do is look at the gain of this common source, AV. So here's the common source amplifier, which was shown in the last slide. This right here is the AC model, low frequency. So in that particular case, this of course becomes ground, right? So that's why this RD right here goes directly to ground. But since we're dealing with low frequencies, it's really not a good idea to get rid of your capacitors, right, due to impedance issues at low frequencies. So keep those there. but that still becomes like a ground, a virtual ground, okay? Um, and this right here, that goes to ground as well, but it gets in parallel with this R1, so that's where this RG is right here. So this RG is R2 parallel with R1, okay? And this is the small signal model where we take the FET right here and just replace it with this small signal model right here, because we're assuming that we're operating in the linear range and there's a very small variation in input signal, and that's linear. And so here's the linear relationship. Okay. So in dealing with this right here, we'll come up with our analysis. So at low frequencies below midband, the impedance of the capacitors can no longer be assumed to be negligible, and they must be retained in the AC equivalent circuit. To determine the behavior at low frequencies, we replace the transistor by a small signal model right here. And since the stage has an external load, we neglect R0 for this right here. Okay. So in the frequency domain, here's the output. So we're talking about this voltage right here, and you can do that with current division. So this voltage is the current I0 right here times R3, okay? And this I0 by current division is, well, here's the current source right here, and this current is being split up right here, right? It's going through RD, and it's also going through this branch right here, capacitor and resistor. So let me just remind you guys about current division. So if I can remember it. So let's say we have something like this. We have some current source. Let's call this the total current coming in this direction. So here's IT going in there. And let's say we have some resistors here, or some impedance values. And so we have this one, we'll call this one, this is one we're interested in. And these are just some other ones, R1, R2, R3. Let's call this R0. We're interested in this current right here, R0, right? So this right here, we'll call this like the sum of these R's. Well, what's probably like a bad way to label that. So let me just call this RT, the total of that resistance looking in that direction. So this current I0 is equal to the total current, the total resistance looking at that and now along that direction divided by RT plus this resistance right here times what you're starting with. Yeah. I think that's right. You guys agree with this? Yeah? Okay, cool. All right, so that's what's happening right here. And so that's where we're getting this expression from. So this right here is the current, is the voltage-controlled current source. It's negative because it's going in this direction. I'm sorry. It's negative because this current is going in this direction, and that's in the opposite direction of that. And this resistance right here is everything else besides that. And then the rest is this plus this branch right here is the resistance you're dealing with going in this direction, which is the sum of those. Okay, so what you do is take this and you plug that into here. And in doing that, then you get this expression, right? So this IO is substituted with this stuff right here. Um, and also you have this voltage VG, which is that right, sorry, VGS, which is that right there. And so that voltage is a voltage between the gate and the ground. So here's the gate, I'm sorry, not the gate and ground, but the gate and source. So here's the gate voltage, here's the source voltage. And so VGS is equal to VG minus VS. Okay, so we're going to find both of these. And so this VG can be found by voltage division. That's this right here. So it's this resistance divided by both of these right here. So that's where you get your VG right here. And RI and C1, that's this contribution right there. You can multiply the top and bottom by SC1, and then you get this expression right here. And this is important. This is in terms of VI, because when we get the gain, we want V out over Vn. So here's Vn right here. So keep that in mind. For Vs right here, we get that by KCL. And so that's this right here. And so you have this current GMVS going into that branch. You have this current going out, and that's Vs minus 0 divided by 1 over SC3. That's this right here. You also have this going from Vs minus 0 divided by Rs, and that's this expression right here. Okay, and this right here is this expression. And so if you factor out your Vs and solve for it, you get this expression. Okay, and so this expression right here, VGS, which is VG minus Vs, substituting what we've just seen before, we have this expression, and then you can simplify that to this, and then simplify that even further by dividing by S over C3, and you get this right here. Okay. Oops. Oh. What was that one more slide? Okay. I know what was on the slide. So what was on the slide was that I took this V out and I divided it by this expression that I had including this Vn. And then that right there was the amplitude of AV of that circuit. And then from there, we would then apply the analysis that we did above, where we looked at, let me go back to this equation. Yeah, right here. So I was going to show you how we got that from the circuit, right? And then what we did next is do this, where we took those expressions and then we found out what A mid was and also what FL was. And we assumed this to be 1, FH. Okay, so we assumed that to be 1, and so we basically had this expression and that expression, and this was in terms of S. Okay, but something happened, but I'll load it up online and show you guys. Okay, so any questions? All right, great. All right, I'll see you guys on Monday.